Hi everyone. I think we can get started because it's just about gonna be like 5:10. Um just quick update on how everything's going. I apologize. I missed Sunday's class. I just had some church event to go to and it kind of lasted the entire day. So let's do okay, so don't not to worry, I'll make up that Sunday with an extra class. But we'll just continue on. Basically the stuff I was gonna cover on Sunday, I'll just cover it now and then we'll just push it we'll just push stuff back about like just one or two classes. So it shouldn't be that big of a deal. So just some housekeeping stuff. Dr. Seen has requested me to share with you guys that Google Classroom Google Classroom link. So I'm pretty sure you guys had enough time to log in or not log in, but yeah, just click through the link and then join the classroom. I posted the link in the chat, um, so yeah, just do that as soon as possible so we can start like when you have your first assignment this week. You'll be able to submit the your solutions to the Google Classroom. Okay, yeah. So for today's class, what we're gonna do is we're gonna go over sorry, let me stop sharing this whiteboard. And then so today basically gonna go through is these slides over here for the first hour, so up until like 6 o'clock. Then after that, what we're gonna get into is your first assignment. So it's right here. I think I did post it in the Google Classroom Drive. So if you guys want to go like during class, just take a look at it or download it to have a copy of it on your side. And yeah, so I'll explain more as the like around 6 o'clock. But um, so let's get into this PowerPoint. So yeah, so just some review. Like last on what was it Wednesday, we got into the topic of kinematics and just some introduction, like physics intro stuff. So we talked about quantities, units, vectors, displacement, velocity, acceleration, kinematics, and graphing motion in one direction. Now, this class we're going to go a little bit deeper and then explore some different situations where you have to kind of apply the kinematics equations to different problems and whatnot. So yeah, so again, this is just a refresher. A vector, it's a quantity that has both magnitude and direction, so you can basically measure a vector. Scalar only has magnitude, so there's no direction in a scalar. So you would never like if you're labeling like certain values, you usually denote the variables with like a small little like arrow on the top. Those are only for vectors. For scalars, you don't need to do that because there's only giving you the magnitude. There's no direction. And here's just some examples of what vectors are and what scalars are. So displacement and distance. Um, Displacement, it's kind of, yeah, so I guess some students kind of get confused with displacement and distance. And I think when you read the problem, I guess the best advice I can probably give is just read the problem and see what they're kind of asking, because there will be displacement type questions and distance questions, and then applying the different formulas obviously will impact your final solution. So a displacement is a vector, velocity is a vector. Velocity and speed, again, these are interchangeable. I think a lot of people confuse the two. But as we go through more and more problems, you'll see like what we talk about between velocity and speed. Acceleration and time, obviously acceleration has direction. Time, it's pretty interesting. Like, some scientists may argue that no, time does have a direction, but really time is just very like circular, right? Like, so it's just always going in that one kind of clockwise direction, if you can imagine it, but it's just in one sorry, not direction, it's just constantly going in that same pattern. But some scientists argue different. So mass and weight, we talked about, I think we talked about in the last class, but this is very important too, because like when we get into the like Newton's laws and like gravity and space and whatnot, mass of the objects usually change depending on um, like usually usually like how what other factors are influencing it. So in this case, gravity would impact mass a lot, and it would also impact the weight of an object. So like here I wrote like on the moon, your mass would be the same, but the magnitude of your weight would be less. And what this means is that basically like the total amount of mass that you have here on Earth doesn't change, but the way that mass gets distributed out, like, or the way, that mass gets kind of like, distributed on the moon, for example, is gonna impact like your total amount of weight. And that's just because you don't have much gravity pulling you down, right? So your mass could maybe be a lot of like a high percentage of it could just be in your upper body, and then when you're only when you're on the moon though, like not when you're on the Earth. So yeah, difference between mass and weight. Usually these types of questions, even for like vectors and scalars, like these questions I'd put like a true and false, or definitely multiple choice on the final exam, but that would be the most I would do for these types of questions. So vectors, yeah. So we talked about like how vectors show direction. That's why we give these we give them like a little arrow, or in this case it's a pretty big arrow, but it represents in this case how much velocity this object is moving at, and at what angle, which is I guess 42 degrees and 5 meters per second. So yeah, the length of the arrow represents the magnitude, aka how far, fast, or strong, depending on like the type of vector. I don't really like, I don't really care if you shade it darker to show that this vector is stronger than the other. Like I'm not that, as long as I see an arrow and like some coloring with it, that's I'm okay with that. Yeah, the arrow points in the direction of the force, motion, displacement, is often specified by an angle. A lot of the problems you guys will be doing, not only in grade 12, but also in like your first year, is going to be in 2 dimensions. So there will be an angle always involved in your problem sets. It just makes the question more complicated. Not there is no significance to having 2 dimensions versus 1 dimension kinematics, because the equations are often the same. It's usually just adding more variables. So so units are not the same as quantities. This is true because let's say a quantity in this case is displacement, and the unit would be distance. So you wouldn't even, there is no units to represent displacement, but there is a unit to represent distance. Time, seconds, obviously velocity and speed, acceleration. So this slide is basically just making sure we are all on the same page with notations, and these are the only notations you guys will be worrying about for this for these types of problems. Nothing more. Like you won't have to do like sigma or beta or alpha or gamma, none of those. But I do think in your, like maybe if you guys pursue more physics in like second and third year, you guys will get introduced to that. So right. So yeah, so when I mean we did talk about on last Wednesday scientific notation. I do want your final answers to be in like powers of 10. So this decimal notation is what I expect to see on your assignments, final exam, midterm, or any solution you submit. Just make sure you guys have it in this notation. So yeah, just again, just a refresher, kinematics, basically study of motion. We'll mainly dealing with position, x, distance, how far something's traveled, and then displacement, where you ended up related to where you started. Um, so so distance and displacement. So we're gonna dive a little bit deeper into like the differences between these two words. So let's say you drive the path and your odometer goes up 8 miles, aka your distance. So that's like your if you guys drive, you'll know like when you drive a certain distance, there's like that all those bunch of digits on your front of it's usually between like the two the two speedometers. It's like right in the middle. So basically what that means is that your displacement is usually going to be not shorter from the distance where you started. And it's a little counterintuitive, but this diagram kind of does does it well where, you know, you if you drove in a circle, like would that be the same amount of like did you essentially, if you drove around a circle, did you displace or did you go anywhere essentially? And the answer is no, because you landed up right in the exact same spot. But the distance traveled is going to be is you're going to have some distance travel because you still what like you still did something. Like it's still, even though if you drove around a circle on your car, it's not going to be like, oh, because we drove around a circle, we didn't you don't have you didn't travel any distance. And essentially that's not true, because the car will definitely will like track how much time you spent on the road and whatnot. So yeah, that's just kind of an example between distance and displacement. Um, Again, we're gonna go a little bit deeper into speed, velocity, and acceleration. Basically, all those terms that we saw in the like first couple slides, we're gonna just go a little deeper on how they're different and like how they kind of relate to each other, but they're not interchangeable. So speed and velocity, you can't use them in the same context, but they will be definitely like solvable. Like you'll be able to solve speed for velocity and vice versa. So speed in this case is how fast you go. Velocity, because we represent it by a vector, is how fast and which way the rate at which the position changes. So this is interesting because a lot of the problems will always I'll always give you velocity. I'm never going to give you a value for speed because that's not what we're interested in. Average speed is basically distance over time. And it's average meaning like if you just hide the word speed and you just take average, you're always going to take a ratio of two numbers. And in this case, because we want to know the average speed, it's basically the ratio between the distance traveled over the amount of time it took you to travel that distance. Acceleration is a vector. So I highlighted the vectors in blue and the scalars in just regular black. So acceleration is how fast or your speed, basically your change in speed. So oh sorry, the rate at which your velocity changes is your acceleration. So when you think of acceleration, just think about what is my velocity, like how is my velocity changing? And that's the description of acceleration. On the final or midterm, I'd definitely probably put this as like fill in the blanks. So I'd be like speed, oh sorry, I'd be like speed, and then like a blank, or I'd put like how fast in which way the rate at which position changes, and then I'll put like a blank space. So it's like can define which one means what, and I can probably give a word bank or something like that, but we'll see. Okay. Yeah, so like we talked about, here's just some more examples on speed and velocity. You guys can take a look at it after class or like when you guys are studying. Speed versus okay. So yeah, this is just going over again what we talked about, driving in a circle versus driving from point A to point B. Okay, so Acceleration, aka how fast you speed up, slow down, or change direction. It's the rate at which velocity changes. So here's two examples. You're gonna notice is that obviously one's in miles per hour, the other's in meters per second, but that's not what we're looking for here. What we're looking for here is on the table on the left, we see our velocity. Just look at the numbers increasing, right? So, and then on the table to the right, you're going to see the numbers decreasing. So anytime you see that those two, like intuitively, you should think about, okay, if my velocity is increasing, I'm definitely going faster. So I'm speeding up. But if my velocity is decreasing, that means I'm slowing down. So like in the one case, you could model it as, okay, a car is going, accelerating, and then model B would be a car deaccelerating. And we're going to denote the deacceleration with a negative. And then obviously if you're speeding up, you'll have a positive, but you don't need to put the positive sign. If it's positive, just leave it as just a regular 2. However, if you are deaccelerating, you're going to need to put the negative in front of your answer. So and again, they're just calculated that by just taking the total distance traveled divided by time, and then going from there. So okay, right, and then again, this table just goes to show the sign chart, but I'm pretty sure it's straightforward. Um, okay, acceleration due to gravity. One sec. Okay. Okay. Yeah, this slide, I'm gonna let you guys read it on your own time. It's not nothing too serious. But I probably would put like one question on the midterm or final. Just basically, but this would be a short answer question. It would be extremely open-ended, so it's nothing you guys. It would be more of like I'd gauge the question to be like more of an intuition, see where you guys are thinking about the acceleration due to gravity. So, okay, so this is probably the most important slide of this PowerPoint, mainly because these are the only 4 kinematics equations you guys will be using this semester. I think I wrote it a bit differently, but it's still holding true where these two, like everything you see in blue, is going to be basically a vector, like where you solve for vectors, and then everything in black is basically going to be stuff where you solve for scalars. Now, it could be you guys could have seen something different, and again, they're all the same. It's just like you derive the equations a bit different. I think every every class does it different, but at the end of the day, they're all the same as long as there's 4 or 5 variables in each question in each equation, then there's enough to solve the problem set. So I won't go through the derivations with you guys because I don't think it's that important. But I definitely will not ask you guys to derive these equations on the midterm or final. You guys, this will be given to you guys. But if you're curious, I just mention it in those 2 slides. So let's do some sample problems. Wait 1 sec. Oh, I should have hit the answers, but that's okay. Okay, so you're riding a unicorn at 25 meters per second and come to a uniform stop at a red light 20 meters away. What's your acceleration? So how about this? I'm gonna give you guys 5 minutes to try these questions out, and then I'm gonna switch my screen to the whiteboard, and then we'll take up the answers on the whiteboard. But in the meantime, if you guys want, you can sorry, not if you want. Could you guys just post your answers in the chat? Not now. I'll give you guys like 5 minutes, but yeah, when you get your answer, just post it in the Zoom chat. Oh, wait, sorry, I didn't realize I stopped sharing my screen. 1 second. Um, Okay. Okay, let's go through the first question. So I just went pretty straightforward. We'll have v2 squared is equal to v initial squared plus 2ad. And in this case, what we were trying to solve for, 1 second, let me pull this up. Right, so 25 unicorn riding at 25 meters per second and then stops at a red light 20 meters away. What's your acceleration? So in this case, what we needed was we know that we have our v initial is going to be what was it, 25, I think 25 meters per second squared, so 25 squared. This is going to be 0. The final velocity when it comes to a stop is always 0. Plus 2a is the variable we're trying to solve for, and then times it by 20. Okay, so rearrange it. You're going to look at minus 50 is equal to 2 times 20 is going to be 40a. So your acceleration is going to be negative, and that makes sense because this unicorn should be slowing down. Cancel those, so you're just left with I don't know the decimal to that, but it should be I don't know, like minus 1.25 would be your answer. Was A. Okay, and then we denote our A acceleration with a little vector. Question 2. I was reading the question. We didn't talk about impact velocity, but yeah, I guess it's okay because I'll just write out the solution, and then you guys will have it within your notes. So we'll have height is equal to v initial times t plus I think that is a yeah. So plus 2g t squared. So g is just gravity, which is like technically our acceleration because that's the only variable we have. So I'm going to rearrange the b initial. Obviously, this goes to 0 because there's no initial speed. The 2's will cancel out. So you're just going to be left with h is equal to, sorry, the 2's do not cancel out. So you're just left with h is equal to gt squared over 2. Now I want to isolate for t, right? Because we asked for instantaneous velocity and the time it took for the ball for, sorry, the impact velocity and time. So I know I have t at squared, so I'm going to undo the square by square rooting both sides. So you're going to have, actually, yeah, that's fine. You're going to have, yeah, you're going to have square root of 2h over g. And I kind of skipped a bunch of steps, but here, one sec, I guess I can, because it was kind of getting messy. So what I have here is basically, h is equal to gt squared, right? Over 2. And then what I was trying to say was I want t by itself. So I'm going to multiply both sides by 2 to divide, to basically like undo the division. So these guys get canceled. So you're left with 2h is equal to gt squared. And then just to get rid of that square root, I'm going to, just to get rid of that squared, I'm going to square root both sides and then divide by g. So you'll get, I can just do this in one step. So you're just going to get 2h square root 2h over g is just equal to your time. Now I'm gonna leave this question unsolved, only because I want you guys to go through the steps. So I already got you the formula for time. Now it's just you have to the goal of this exercise is to make sure if you guys can plug in the numbers properly, and then able to get the final solution. So, and kind of see if your calculators are all working. So that's the formula used for time. And then for instantaneous velocity, I'll also give you guys the formula. Velocity is equal to v final is equal to v initial plus gt, or in this case, I could put, instead of putting g, I could put a, but I think it's the same. So, well, whichever you prefer, that doesn't really matter. So the instantaneous velocity, impact velocity is going to be v is equal to gt. So there you go. So yeah. So just find those two solutions and just post it on. I think there's a discussion board on Google Classroom, but I'll find it. Okay, great. Don't worry about the third sample problem. I think it's kind of useless. Well, there's already enough of that in your worksheet, so I want you guys to get started on the worksheet soon. So, okay, that's pretty good. Okay, let me go back to the slide. Wait. Okay. Okay, so multi-step problems. One second, let me see. Okay. Yeah, so multi-step problems, we're not going to have time to go through this in class today, but when you're studying for like your final, or when you're studying for like the midterm or like unit 1 test, definitely go back through these slides and try and solve these problems, because like I said at the beginning of like on the very first class, like I don't like giving surprises, and none of the questions you see on your final, midterm, or even on the unit tests are going to be anything different than what you see here in the Google slides. So I'm even willing to go with this. I'm not even going to say it, but same numbers. But just make sure you know how to get to this final answer. And if you don't, just send me an email or ask me a question, and then we'll get the answer solved. Okay, graphing. So basically, what you're gonna, like on a test or final or whatever, you're gonna be asked to usually graph some of the problems that you solve, and rightfully so, because it's kind of a good exercise to visualize what you're solving for. So This is just a typical example. So let's say A, you start at home, and you proceed forward slowly. So even though you're going slowly, you're still making like distance, and you're still um gaining um positive yardage or positive distance, so that makes sense. Now, B, not moving, position remains constant as time progresses. So this is interesting because if you have to ask what's happening here in segment B, you're still moving forward, aka like you're still you're not moving forward, you're still exerting time, but you're not going anywhere. So like your distance, in this case that represents X, you're not moving farther than where you started. So that to me, it's like that could be like multiple scenarios. One thing I can think off the top of my head would be like, um, yeah, I'd be like, okay, you leave your house, you go to the mailbox, and then you're just staying at the mailbox. You're still spending time, but you're still at the mailbox. Now, it turns around, goes the other direction, passes home quickly. So when you pass the y-axis and go into the like opposite or into like the other like side of the graph, that means it could be multiple things. But in this case, you did pass your original location, and then anything else could happen after this. You could probably go in a different direction, or like, yeah, just anything could happen. But as long as so on test or final, I would just ask like, describe what's happening in this graph, and then be color coded the same way. So yeah, as long as you can understand what's happening, then I think you're pretty good. Um, right. So that was with displacement and time. Now we're going to graph with respect to acceleration. So acceleration, like we said, is your average rate of change of velocity. So um, it is curvy wise because when you get into calculus, you'll probably do tangents and a slope of a tangent line. So what that is basically you want to approximate the area underneath the curve, and what that does is basically tells you exactly what was happening from let's say this position to this position. In this case, it's from B to C. Doing that, you obviously we can't to get the area underneath this graph. We don't know any shape. Well, this is kind of like a half circle, but there's no shape that we know that we can calculate there underneath this curve. So what we do is we basically break this piece up into a lot of smaller triangles. And from those triangles, like they all have like top positions, like aka like the like on a triangle, you know how it has like the top of the surface has like one point and then connected to another point. Well, yeah, that those 2 points is what we're calculating the tangent line of. So again, this is just an example of acceleration. So uh, I would ask again like what's happening in this case, and it's pretty straightforward. You start home, you start from rest, and then you head home right from home. You pass home gradually, slow to the top, still moving north, turn around, gradually speed back up, going down, and you can continue heading south gradually, slowing to a stop near the starting point. So yeah, I'm just start here. Okay, tangent lines. Oh, okay, great. So yeah, I don't think I'll ask too many questions on tangent lines because then that's where we're getting into calculus and we're not really getting into physics. But just know that we use tangent lines to approximate the area underneath the curve. Decreasing negative. So the concavity of a graph, when it comes to position and time, upwards or concave up means it's a positive acceleration. So like usually at the start, you'll always see like a concave up kind of pattern. And then concave down means negative acceleration. So usually like slowing down, obviously, and then yeah, but this is a weird shape for an acceleration. It's usually like up, 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 a little bit of dip, but it keeps going up, up, up. But we'll see. Inflection points, peak or valleys. No, wouldn't do too much because then that's not too many. Then I feel like we're just talking about the curves, right? So it's like calculus. Wouldn't want to get too much into that. Okay. We'll go graphs. Okay. How many more? Oh, is that it? Okay, sweet. Okay. Right. So graphing, you won't have too much to graph in this class, or yeah, in this class, mainly because it's we're not an art class. I don't really care if your lines are straight, but these people, sorry, the previous professor that made these notes, which I borrowed from my first year class, um, he was pretty serious on making sure your lines are straight and when you graphed and stuff, but I didn't lose marks for not being neat or whatever, as long as there was a general pattern to my graph, then everything you'll get like full grades. And as long as you label your graph too, I think labels are very important. Like in this case, like you can even see that you can add labels virtually anywhere on a graph as long as they're not overlapping and they're not hard to follow. Um, Always treat a graph like a roadmap, or treat a graph like a map, and always like when you make a graph, make it for like the lowest common denominator. Think about like if someone was to see this graph or someone were to see this graph, like what would they like what information could they get almost instantaneously, like without even having to think about um think about like what they're looking at. And I think if you can do that, then you're really on track to doing really good. Not only in graphing, but in like other courses and other classes. So yeah. Okay. So yeah, and again, we were just talking about like this would be like a lot more calculus, but I wouldn't ask to find the area underneath the graph. I would mainly just ask, in this case, describe what this graph is doing. Can you draw a similar graph with this scenario, or given this scenario, could you model this in a graph? And it would be like, for example, I took my dog out for a walk. We went down this path, went down this path. We stopped. We stopped by to have like um, a cookie, and then or treat, and then we made our way back home. So like, what would be the graph um, that would model that situation? Would be an example. I'd put on a test or assignment or final. Um, right. So graphs of the ball being thrown straight up. Yeah, so this would be, I would put this as a multiple choice question. But again, you wouldn't be asked to draw like these kinds of situations. It would just be given this situation, what's happening, and is this the right model for this situation or not? Graphing practice, again, when I go back and edit these slides, I'm gonna take out this slide so you don't have to worry about it. This is a good kinematics practice. I'll keep this slide in because again, I'll automatically I see there's um, you know, there's some units and conversions that you guys have to do. So practice this question for sure when you're studying for this unit 1 test. But oh yeah, unit 1 test, I forgot to tell you guys. I think it's one sec, let me just check the schedule. So right, so the way it kind of works is that when you submit your first assignment, which is going to be on this Sunday, the 17th, um, the unit 1 test would be the week after that. So it'll be on Wednesday, the 27th, but I'll make an announcement and we'll go from there. But yeah, we're trying to get a unit around two units per month done. So kinematics we go through pretty quick, so it's not too hard. Okay. So yeah. Um, and yeah, it's the same thing. If you guys, when you know you practice this and you get stuck or you need some help with a step where you missed or whatever, just again send me an email and I'll be happy to help you out. Uniform acceleration, pretty standard. Again, when an object starts from rest and undergoes constant acceleration, position is proportional to the square of the time. This is interesting because that means that the object is moving at twice the not the square of time means it's doubling its time as its position changes. So for every let's say you're traveling at a constant speed of, well, actually, no, it makes sense for gravity, right? So 9.8 meters per second squared. The seconds is squared because every 9.8 meters that something travels due to gravity, it's going to be double that time. So for it to travel 9.8 meters, it's going to take double that time to get to 9.8 meters, if that makes sense. And so this slide I'm just really trying to drive home there's a difference. That you will have some questions that say uniform acceleration, and you have to treat it differently because you'll see there's just different components to it. So spreadsheet problem. Oh yeah, okay. Don't worry about this spreadsheet problem. You guys have enough practice problems to work through. But this could be a bonus. I could add this as a bonus if you guys want, but we'll see. Let's use kinematics equations to answer these. A mango is dropped from height h. If dropped from a height of 2h, would the impact speed double? So they're saying basically if you double the height, would the impact speed double? Would the airtime double when dropped from a height of basically 2 stories? So the impact, so the airtime. Yeah. So intuitively, the impact speed's not going to double, even though you go higher. And why is that? Is because it's the Galileo experiment where I think he dropped a golf ball, or sorry, not a golf ball, a bowling ball and a feather, and they both landed at the same time. Right. Sorry. The impact speed would double because you're going higher up, which means that the force of gravity pulling you down is going to be twice as much. So yeah, the further, that's why like dropping from the CN Tower would hurt, or would hurt way more than you just dropping off like a one-step ladder, right? Even though like the time is basically the same, your impact speed is going to be double. So let's say a mango is dropped or thrown down at speed v. If thrown down at 2v from the same height, would the impact speed double? In this case, because we're dropping it down from two velocities from the same height, the speed would double. Would the airtime double in this case? No, because we haven't adjusted the height. So time remains the same. A rubber chicken is launched straight up at speed v from ground level. Find each of the following if this launch speed is tripled in terms of any constants and v. So 9v squared over 2g, hang time, impact speed. Yeah, don't worry about this slide. Just these 3, 1 and 3 is most important questions, or these 2 questions. Okay, sweet. So that's it for this slide. Now I'm going to, 1 second, switch my screen to the, okay. So, okay, so can everyone see my screen? Everyone's seeing the document now. Um, okay, so right now I believe it's 5:59, so it's 6 o'clock basically. You're gonna have the next hour. It's gonna be, if you want, you can collaborate with your classmates, ask questions, send each other a message if you need help. But more importantly, you can ask me if you need help. Basically, you're gonna have this hour to work on it. You can use your time however you want. If you want to finish it, submit it to me by the end of class, great. If not, it's gonna be due, I guess I should write it down. So this is gonna be due on, so due, September, what's the date on Sunday? September 17th, so September 17th, Sunday at 1 p.m. I'll make the deadline at the end of class. Just submit. Okay.
Okay.
Right. So let me just see. Right. So there's 20 questions. This assignment, I believe, is worth. Yeah, it should be broken down um in the first like week zero lecture slides or Google slides. They should be there. Oh yeah, pretty straightforward. Again, if you guys need any help, I'm here at my computer, so I'm just gonna mute my mic, but I'm still here. So if you need help, just send me a quick message, and then I think I can take people to a well, what's it called? Breakout room, where you can share your whiteboard, and I can share my whiteboard, and then we can have a discussion there. So, okay. You guys are good to go. You guys are good to start working on this assignment, and again, ask me any questions if you need help. Hi, sorry. I'm just reading the comments in the messages in Zoom. I don't think I posted it. I think I posted it. So if it's not there, give me 1 second. I think I have to that's weird. 1 second. Okay. Give me 1 sec. Hold on 1 sec. Okay. I think I shared it. Can someone just in the chat confirm if they see it now or it, can you guys see it yet or is it not there? Okay, sorry about that, guys. One sec. So I'm sharing the link in the chat. I'm just I think I'm missing some permissions on the Google Classroom side. So I'm just gonna share the link for the assignment, and then I'll share the link also to the lecture notes that we took in week 1, and then I'll share the week 2. But I think if you click into that link, it should take you to the yeah. Oh, okay, one second. For both links? Okay, give me one second. I just got to change the okay. Okay, I'm just changed the permissions there. I also made the file offline, so I think if you don't have internet connection or whatnot, you can still see all the information and details. So um hmm, okay. There is okay.